Today's lesson is on spring energy. First of all, with spring energy, there is a law called Hooke's law. This law states that the spring force is equal to the spring constant times the distance. Okay, let's talk about each of those components. The spring force is like how much force the spring is going to give. So you push down a spring and it pushes back. How much force is that going to give? The K is the spring constant. And as far as K's go, if you look over here in the margin, a stronger or stiffer spring is going to have a high K value, whereas a looser spring is going to have a low K value. And then X is the distance that is compressed. So if you have a spring and you just compress it, I don't know, depending on how big the spring is, but you just compress it like a foot or a meter. How much energy will that have compared to, okay, you take that same spring and maybe it's a really big spring in a machine and you compress it 3 meters. How much force will that give? So the amount of force is dependent both on how stiff the spring is and how much you compress it. That's what Hooke's law is saying right here. If you look over to the right, I have these diagrams, and these diagrams actually come from the book out of page 143. It is also a concept at the edge of the page here that you would need when you do your homework. We're going to do number 31 in the homework, and when you do number 31 out of the book, this is what the book is referring to. Let's continue on with Hooke's law. So here we have Hooke's law, and underneath here it just explains what all the variables are. So K is the constant of the spring, called a spring constant, and X is the displacement of the stretched or compressed spring. Question 16 says, what are the units of the spring constant? Let's look at our equation. Okay, over here in the margin, I just took this same equation, and if you look at what I have here, I basically just took this and divided this side, divide by x, and took this side and divide by x, and that gave me this equation over here. I just divided by x so that I was solving for k rather than solving for the force. Okay, so because the reason I did that, what are the units of the spring constant? If we look at this equation, well, what do we measure force in? Newtons. And what do we measure distance in? Meters. So the units of the spring constant is newtons per meter. That is the units that we will use. So anytime we talk about spring constant, we will label it as newtons per meter. Number 17, if the displacement of the mass is in the negative direction, what is the direction or the sign of the spring force of the restoring force? Let's take a minute to think about this. Let's draw a little diagram. Let's say you have a spring like this, and you compress it, and let's say you compress it to the left. Okay, then we have this thing called the restoring force. And the restoring force, what that means is if it goes back to its original shape. Because that's what the spring wants to do, right? If you compress the spring, it's going to go back to its original shape. So if I have this spring that's kind of stretched out, and I compress it to the left, well, the restoring force, it's going to want to spring back out the other way. And so the question is, if the displacement is in the negative direction, so if we call this a negative direction, then what direction is the spring force? Well, the restoring force is going to go out this way, and it's going to go in the positive direction. We just want to make sure we understand what's happening, that when you compress it to the left, it will, when you let go, it's going to bounce back to the right. That's all that's talking about. In addition, over here in the margin, the X that we're talking about can be either direction. And different springs act differently, and hopefully we'll try to explore some of those. But you can pull a spring out, or you can compress a spring. And some springs that you would pull, I mean, you can do either one to either type, but of course sometimes you would kind of break the spring by pulling it too hard or pushing it too hard. So as far as one that you pull, think of, for instance, a slinky. And when you stretch out a slinky, what does it want to do? Well, it'll spring back into place. On the other hand, we have springs like were in that little jumpy toy we had. And the spring in the jumpy toy, you press it down and it springs out. So we have two different kinds of springs, and some of them you pull and some of them you push, but the restoring force is always going to be the opposite direction. Okay, number 18, the mass eventually gained kinetic energy. Where did this energy come from? In other words, we're talking about we compressed the spring and then it bounced back. Where did that bounce back come from? Well, the bounce back came from the spring itself. That you yourself stored work in that spring. You did work, and work is change in energy. So when you did the work, you pushed the spring, and that added energy to your spring. And that is now potential spring energy, which we abbreviate with a U sub S. That means potential spring energy. Another phrase for that, sometimes we call it spring potential energy, sometimes we call it elastic potential energy. So either one of those terms, those are interchangeable. Sometimes our book talks about elastic, sometimes it talks about spring. So the elastic potential energy associated with the spring force is this equation. Our book uses the PE, that's potential energy. The AP likes to use U sub S, that is still potential energy, but it's with a sub S means spring potential energy. Now look at this equation. The equation is a lot like 1/2 mv squared, but instead of an mv squared, we have a kx squared. And remember, K stands for the spring constant. That is a number associated with the spring that tells us how strong or loose that spring is. And X is how far you compressed it. How far did you smush it down or pull it out? All right, so now when we talk about total mechanical energy, and we say total mechanical energy, what are we talking about? Well, now when we say total mechanical energy, we are talking about three things: spring potential energy, gravitational potential energy, and kinetic potential energy. All three of those are part of our mechanical energy. And so when we do our LOL charts, and we saw this already, when we first introduced LOL charts, we saw this already. We need all three of those: potential gravitational, kinetic, and spring energy. And we're familiar with that with our LOL charts. I want to take a look on the right-hand side at this diagram. This is something, again, comes from the book, but I want to kind of go through and explain it. So if you'll look, the first picture, and they're calling this section A, this first picture shows the spring, and as the spring is here, it is in like its natural state. It is neither compressed nor pulled out, and so it is just here in its normal state. Now you can see this hand is about to push this mass towards it, but right now it's in its normal state, neither compressed nor stretched, and that's why X is 0. So when it's at equilibrium, we call that equilibrium, that means X is 0. Now, in the next picture, we take that mass and we push it against the spring, causing the spring to be compressed. And so the distance that spring was compressed is called our X. So I would like to think of it as a delta X, but we just call it X. So that is just showing us how far did the spring get compressed. Well, here our potential energy was 0, right? Here it didn't have any potential energy because it was not compressed. In addition, it didn't have any kinetic energy either because it wasn't moving. We go to option B, and now it is compressed, and so now it has potential energy. That is 1/2 kx squared. That is, the energy stored there depends upon the spring constant, how stiff it is, and the x, that is how much did we compress it. Kinetic energy, again, it's 0. It's not moving, so kinetic energy is still 0. And then in the third part of the diagram, we let the spring go. And when we let the spring go, that's going to send that mass sliding out the other way. The potential at this point, we could go back to our LOL chart. The potential at this point is 0 again because the spring is back at equilibrium. It bounced back and now it's back at its normal state. The kinetic energy is how fast it's moving, 1/2 mv squared. So if we did an LOL chart, I think we could skip the LOL for part A, but for part B, if we had kinetic energy. Now notice we don't need gravitational because it's not going up and down. We will get to springs that go up and down, but our springs are not going up and down right now. They're just going side to side. So we don't actually have gravitational potential. What we have is spring potential. And so over here, we're going to have our final situation with the same things. So at the beginning, it does not have any kinetic because it's not moving, but it does have spring potential because we've pushed it in. At the end, it has a lot of kinetic because it's moving, but it doesn't have any spring potential because the spring has gone back to its normal state and it's not even involved in the mass anymore. And so you can see how we would set up our equation. We would set it up with 1/2 kx squared is equal to 1/2 mv squared. Because those each are 0, this one is the spring energy, this one is the kinetic energy. And we would see that in our LOL charts as we go along. All right, let's turn the page. If we look at this example, a massless spring is between a 1 kilogram and a 3 kilogram mass as shown above, but is not attached to either mass. Both masses are on a horizontal frictionless table. In an experiment, the 1 kilogram mass is held in place and the spring is compressed by pushing on the 3 kilogram mass. The 3 kilogram mass is then released and moves off with a speed of 10 meters per second. Determine the minimum work needed to compress the spring in this experiment. Okay, let's first of all clarify what the 1 kilogram mass is doing. And that is the 1 kilogram mass is not doing much at all. It is basically acting like a wall. That's all it's doing. It's just holding that spring in place. That's all it's doing. It's something to compress against. Other than that, that 1 kilogram mass is not part of our problem. Remember that work is defined in change in energy. And so in the beginning of this problem, we didn't have any energy at all. But when we pushed it, we added work into it. And so now we have energy. And the energy that we have is 1/2 mv squared. I'm not including the spring potential because they don't tell us anything about the K value. But what they do tell us about is the speed. So since they give us the velocity, but they don't give us a K anywhere, this is really all we can use. And this is enough. And so our work is going to equal 1/2 the mass. Well, think about it. Are we using all 4 kilograms? Are we just using 3 kilograms? Are we just using 1 kilogram? And we're only using 3 kilograms because we explained that the 1 kilogram is not doing anything. So it's not really part of this situation. The velocity, we have 10 meters per second, and that gets squared. And so now we just need to pull out our calculator and work this out and see what this comes out to be equal to. And remember that work is measured in joules. Work is a type of energy, basically. We're adding energy, so it's joules. So 150